Today we're learning 4 new theorems, and they're not necessarily about similar triangles, although I'm sure you'll see a connection, but they are all about proportions. These first two are talking about this sort of figure. It looks like a triangle with an extra line added in, but what we're going to look at is these 4 lengths of these little chunks here. And this first theorem says that if these two segments are parallel, then those lengths are proportional. And then the converse is also true. If you knew that those lengths were proportional, then you could say that those little lines are parallel to one another. So let's just do one example of each. This first one says solve for x, and I see that I have parallel segments, so I know that those are proportional. Those little chunks are proportional to each other. X is to 9 as 4 is to 6. You could also set it up as x is to 4 as 9 is to 6. You guys know that proportion is going to be set up a lot of different ways and still get the same answer. And the length of that little piece is 6. So the way this theorem is worded, this piece that is parallel to that other side of the triangle, that divides these two sides proportionally. It doesn't say anything about the length of the actual parallels, but it does say that these chunks on the side should be divided proportionally. And then this is how it would be worded if they were asking you to use the converse. We're going to decide, are these parallel or not? And the way we're going to check is by checking to see if these are split proportionally. Is 90 over 50 the same as 72 over 40? And I think I'll check that by cross multiplying. I could also reduce or divide. 90 times 40 is 3,600. 72 times 50 is 3,600. So yes, those are split proportionally, so I can say yes, those segments are parallel. This example would be a really good one to add to your notes because we're going to find 2 different lengths. We're going to find the length x here, which fits that theorem, right? It's one of those chunks that is split proportionally by the parallel lines. But then we remember that that theorem doesn't tell us anything about the length of the parallels, so we're going to have to use a different sort of strategy to find the length of y. But we'll start with x, which does fit the theorem. Since these two are parallel, I can say that x is to 12 as 15 is to 20. Nice easy solve there. But like I said, when we go to solve for the length of the parallel, we can't use that same theorem. What we can use is what we know about similar triangles. So you guys see that these two triangles would have to be similar to each other, right? Because those parallels are going to give us the corresponding angles congruent. And we'd have that reflexive angle. So definitely by angle, those are similar triangles. And when we see similar triangles, we always draw them out separately, right? So this smaller triangle has an x here and an 18 here and a 15 here. So I'm drawing it out separately. And then the big one has, I guess, MP here would be x plus 12. And y is that bottom side. And this other side would be 35. So in order to solve for y, the length of that parallel, I'm going to have to use these numbers. So the 15 is to the 35 as the 18 is to the y. And if you don't draw those out separately, I just kind of doubt that you would see that 35, unless you're a pro at this already. And we get y equals 42. So just to review, it's much easier to find these little chunks because they're proportional when you see those parallels. But when you're looking for the length of one of the parallels, you have to go with similar triangles. Theorem 6.6 doesn't even look like a triangle thing, but I guess if you drew it a little differently, it could. It's talking about what happens when we have three parallel segments, but it's maybe not always drawn to look like a triangle. Well, this theorem says that as long as those are parallel lines, then you're going to come up with proportional segment lengths here. UW is to WY as VX is to XZ. Or on this triangle picture would be this length is to this length as this length is to this length. And our previous theorem would say that these are also proportional. In this example, they want us to find the length from H to G. Don't use this theorem unless you have three parallel lines though. And since I see angles 1, 2, and 3 are all congruent, there's their corresponding angles, so that tells me that I have three parallel lines here. And since the lines are parallel, I'm allowed to set up a proportion. So the 120 would be to the HG, as the 150 is to 300. I can definitely cross multiply to solve, but I'm seeing that this comes out to 1/2. So I know that that's the ratio that this is following. So that means this side would also have to equal 1/2. So HG must be 240. Again, if that was a leap for you, you could definitely cross multiply, no problem there. And the last theorem of the day is about a triangle. It has to do if you had a ray splitting one of your angles into two congruent pieces. We know we call that an angle bisector. Well, the deal is that these two segments that are formed are then proportional to the two sides that didn't get cut. Let's try this example. Do you see where the angle bisector is? I see the swoop swoop here. And so this PR is cutting QS into two pieces that the theorem says are proportional to the 7 and the 13, the other two sides of that triangle. One kind of awkward thing about this diagram is they didn't actually label this little piece, but if the whole thing is 15, but X is taken up right here, then this would be 15 minus X. We would take this entire 15, but then subtract off that X that's already labeled. So then we can say that the 15 minus X is to X, as 7 is to 13. So it looks like the split here is 9.75, which would leave 5.25 for that other piece. And now we've done an example of each of our 4 new proportion theorems.